Hi, my name is Bhuvan Agarwal, and I'm an intern at Amazon. And so this part of the talk is titled Dealing with the Dearth of Data. So as we've already seen, the public end-to-end SLU data sets are pretty small. And so how do we actually, are there any training strategies or something that we can do to deal with this lack of data? So I'll be presenting my part of cross-modal semantic learning. The idea behind this is that suppose we had the ground truth transcriptions of the audio utterance. We know that BERT is already pre-trained on a large amount of unlabeled text data, and that it can extract good quality embeddings that have semantic information. And so the idea behind this approach is that suppose we could train our LSTM encoder to extract audio features which are close to the features extracted by the BERT model. Then we can say that those features are good, and then we can have a shared classification layer on top of that common embedding space to finally classify the input audio utterance into one of the intents. So here, at inference time, we only use the top branch of this network where the input is the audio and the output is the intent, which gives us this end-to-end SLA system without any intermediate transcription. And so the question that we need to now answer is, how do we actually make sure that these embeddings are close together? So this brings me to the concept of embedding losses, or how do we tie the embeddings from the two modalities together? So one of the ways to do this is to simply use an L2 loss or the L2 distance. So let's say we extract the audio embedding and we extract the text embedding of the same utterance, and then we minimize the L2 distance between those two. But the main drawback behind that approach is that even though it brings the two embeddings of the same utterance together, it does not explicitly move the embeddings of two separate utterances farther apart. And so this idea has been explored in a different field where they tie the embeddings of images and captions for image retrieval and other tasks. And from there, we can get a few ideas of what kind of losses to use. So here, I'll briefly talk about the triplet loss. So the triplet loss takes as input three different points. First is XA, which is the anchor point. The second is X plus, which is the positive instance. And the third is X minus, which is the negative instance. And what we basically mean by a positive and a negative instance is that the positive instance is another utterance which has the same intent. So let's say the anchor could be the audio embedding of make the lighting brighter. And X plus could be the text embedding of it's too dark in here. So even though these two sentences are completely different by themselves, they essentially mean the same thing. And the intent is to increase brightness. X minus, however, is change the light to green, which is completely different intent. And what this loss is trying to optimize is that the distance of the anchor from the positive point should be less than the distance of the anchor from the negative point. And mathematically, this can be written like this, where M is the margin. So it is a hyperparameter. And if the difference between the two distances is greater than M, then it does not contribute to the loss. And these are the results on two of the public SLU data sets. So on the left-hand side, we have the fluent speech commands data set, and the top row is basically the state of the art without any pre-training on separate audio data. And we can see that the model in which we use the triplet loss has outperformed that state of the art. Again, on the right-hand side, we have the SNPs SLU data set. The first row is the baseline model without any cross-modal constraints. And the last row is our cross-modal model with the triplet loss. And again, in both of the two data sets, the triplet loss has outperformed the baselines that we had. So these are some of the qualitative results that we had. So what this is basically is these are the embeddings of the test set of the SNP SLE data set. So we extracted those embeddings and then we projected them down to 2 dimensions using tsne, and then we color coded them using the ground truth intents. The left-hand side is the baseline, and the right-hand side are the embeddings using the triplet loss model. And again, I think it is very clearly visible that the one with the triplet loss has clusters that are farther apart and much more dense as compared to the one on the left-hand side. So that concludes my part of the talk. Now I'll hand it over to Mijao.
Okay, hello, this is Muchao from Carnegie Mellon University, and I will briefly introduce our experiments using the pre-trained automatic speech recognition encoders. So here we extend our baseline model with an encoder of pre-trained speech recognition systems in order to construct end-to-end spoken language understanding systems, because we believe pre-trained ASR encoders will provide good speech representations. Can you go to the next slides, please?
Can you just click on the slide and then do the transition?
Oh, sorry for that. Yes, it works. Yeah, so the ASR speech encoders are pre-trained on large vocabulary datasets like level speech because it contains many unique words. On top of a pre-trained ASR encoder, we then train a task-specific classifier for intents or dialogue act classification using SLU targets. So here is our brief experimental results for using ASR encoders for fluent speech commands SLU tasks. We pre-trained the encoder with transformer and LCM respectively in ESPNet to compare the performance. For pre-training with the transformer, our accuracy score for slot classification achieved 95.21, and for intent classification, it achieved about 88.57, which indicates the pre-trained ASR encoder helps compared to the previous direct model we have talked before. Yeah, so next, let's switch to Roshan for next presentation.
Hi, everyone. I'm Roshan, and I'll talk about combining the two methods that we discussed right